Have you ever just looked around you at the frame of your bike, the fork you eat with, the aluminum foil in your kitchen? Where does all that pure metal actually come from? Because here's a secret. Out in nature, finding pure metal is incredibly rare. So how do we get it? Well, in this explainer, we're going to unlock the chemical secrets that let us turn ordinary rocks, clays, and even seawater into the building blocks of our modern world.
So here's the plan. First, we'll dig into the big problem. Why are metals hiding in the first place? Then we'll look at the two master keys we use to get them out. First, a brute force method called electrolysis, using aluminum as our big example. And then a much more clever approach called chemical reduction, where we'll look at tin and zinc.
All right, let's jump right into part 1, metals in hiding. You know, it all really boils down to one simple but super important chemical concept: reactivity.
Let's start with something you see every day, right? This soda can. It's almost 100% pure aluminum. But here's the wild part. You will never, ever find a nugget of pure aluminum just lying on the ground. It doesn't exist. So what's the deal?
The answer, not surprisingly, is chemistry. You see, most metals are what we call highly reactive. Think of them as being chemically needy. They just don't like to be alone. So they grab onto other elements like oxygen or silicon and form super stable bonds. They get locked inside these chemical compounds. Our job then is to figure out how to pick that lock.
And these metal compounds are, they're everywhere. They're in the minerals that make up the planet's crust, in huge salt deposits from ancient oceans, in clays like bauxite, and they're even dissolved right in the seawater. So see, the challenge isn't really finding the metals, it's getting them to let go of everything else they're stuck to.
To get this job done, humanity's come up with two main keys. The first one is electrolysis. You can think of this as the sledgehammer approach. We just use a massive amount of electricity to force that chemical lock open. The second is chemical reduction. This one's more of a finesse move, where we trick the metal into swapping places with another element.
Okay, so let's talk about that sledgehammer. Our first solution, electrolysis. And yeah, it really is all about using the brute force of electricity to get what we want.
What we're doing here is using a powerful electric current to make a chemical reaction happen that would absolutely never happen on its own. See, when a metal is locked in a compound, it's missing electrons. It's become something called an ion. With electrolysis, we use electricity to literally force those electrons back onto the ion, turning it back into a pure metal atom, whether it wants to or not.
Now, you don't use a sledgehammer for every job, right? This energy-guzzling method is really for the most stubborn metals out there. Remember how we said some metals are super reactive? Well, sodium, magnesium, and aluminum, they are at the top of the list. They form such incredibly strong bonds that a massive jolt of electricity is one of the only ways to pry them apart. And this brings us to the perfect case study, aluminum, and the absolutely brilliant process used to make it, called the Hall-Héroult process.
So here's how this massive industrial process works. First, you take bauxite ore and purify it down to aluminum oxide. Simple enough. But here's the problem. Aluminum oxide has a melting point of over 2,000 degrees Celsius, just ridiculously high. But Step 3 is the stroke of genius. You dissolve that oxide in another mineral called molten cryolite. This one simple trick drops the melting point all the way down to 1,000 degrees, making the whole thing actually possible. Then you just blast that molten goo with electricity, and pure liquid aluminum sinks to the bottom.
Okay, so if electrolysis is the sledgehammer, let's check out our second key, chemical reduction. This is a much smarter, more finessed way to go about it.
Instead of just raw electrical power, this method uses a different chemical element, usually something cheap and plentiful like carbon, to do the hard work. Basically, the carbon wants to bond with the oxygen more than the metal does. So you mix them together and add some heat, and the carbon just swoops in and steals the oxygen away, leaving the pure metal behind. And the big upside? It's way, way cheaper than paying a giant electricity bill.
And this is where it gets really clever. For some metals, that swapping reaction doesn't really want to keep going all the way. It kind of stalls out. But engineers figured out this incredible workaround. The trick is to get the pure metal so hot that it turns into a vapor, and then you just remove that vapor as soon as it's made. By constantly taking away the final product, you force the reaction to keep making more to replace it.
And this trick is a perfect real-world example of a fundamental idea in chemistry called Le Chatelier's principle. And honestly, the assembly line analogy here is perfect. If you keep pulling finished cars off the end of the line, the factory has to speed up to make more, right? It's the exact same concept. By constantly sucking away that metal vapor, we force the chemical assembly line to just keep cranking out more and more pure metal. And I want to be clear, this isn't just some neat little lab trick. This is a huge deal. A process called the pigeon process uses this exact principle, and it accounts for over 75% of the entire world's magnesium production. It completely dominates the industry because it's just so much more efficient. It's a really big deal.
Okay, for our final section, let's look at two more quick case studies for chemical reduction, tin and zinc. One shows us an old trick, and the other a pretty cool new riff on that same trick.
This quote is just so fascinating. It basically explains why we had a Bronze Age thousands of years ago, but the aluminum age is only about 150 years old. It turns out tin oxide is so incredibly easy to reduce that the hot carbon from a simple campfire is enough to do the job. It's chemical reduction in its most ancient, basic form.
And the modern process for making zinc? It's really just a super high-tech version of that ancient campfire. You roast the ores to get zinc oxide, then you react it with carbon, usually from coal, which steals the oxygen. And this is where it all connects. The reaction creates zinc vapor. That vapor is then distilled and condensed into pure liquid metal. By constantly removing the product as a vapor, the whole process is made way more efficient. It's Le Chatelier's principle all over again.
So there you have it. From brute force electricity to clever chemical swaps, these are the fundamental processes that unlock metals from the earth and literally build the world around us. But both of them, electrolysis and high-temperature reduction, they require just massive amounts of energy. And that leaves us with a really big question for the future. What's the next great innovation going to be? How will we make the metals we need, but in a cleaner, more sustainable way?